From SigOpt, an Intel company, I'm Mike McCourt, and this is Experiment Exchange.
A lot of research now is very interdisciplinary. So a lot of these traditional boundaries that you might think of for departments are kind of breaking down.
Today, we have with us Paul Liu, Associate Professor of Industrial Engineering at the University of Pittsburgh. His group, the Laboratory for Advanced Materials at Pitt, works to design and fabricate new materials with unique properties. We will discuss a collaboration between Pitt and SigOpt to design new additive manufacturing strategies to improve the performance of glass. This can include reducing reflection, increasing transparency, and reducing the ability of water and oil to attach itself to the glass. This research was powered by advanced functionality in SigOpt, which includes metric constraints, multi-metric optimization, and a new methodology called constraint active search, which helps to deal with imprecisions that arise during the fabrication process. Ladies and gentlemen, we are back with another edition of Experiment Exchange with SigOpt. Today, it is my great pleasure to be speaking with Paul Liu, who is a professor at the University of Pittsburgh. Paul, would you tell us about yourself, please?
Hi, everyone. So I am an associate professor at the University of Pittsburgh. I joined Pitt back in 2010. I did my PhD at Stanford in mechanical engineering, and then after that did a short postdoc at UC Berkeley before joining the industrial engineering department here at Pitt.
Very cool. Tell me, how are you liking Pittsburgh?
I really love the city. It is great hub for technology and health research. We have both Carnegie Mellon University here, which is very strong in data science, machine learning. And then we also have University of Pittsburgh, which is very strong in biomedical research. If you are familiar with a lot of these livability surveys that are done by Forbes magazine, I think Yahoo does one. Pittsburgh is consistently ranked very high in these livability surveys, so has most of the things that you'd want out of a city: sports, arts, entertainment. It's got parks. The crime is not bad, and it's also very affordable. So you can buy a house here for $200,000 or $300,000, which a lot of cities, other cities, as a professor, you kind of get priced out of.
I can absolutely agree. A lot of other cities are much more expensive, and I've spent a lot of time in Pittsburgh myself. I'm a big fan, and every time I get to visit, I really enjoy being able to spend time in the city. What about now the department? I think that your department has an interesting mix of different things going on. Is that correct?
Yes. So what's interesting is my background has been more mechanical engineering. And when I did a postdoc, that postdoc was actually in electrical engineering. And then I was co-advised by someone, a professor in materials science, when I was a PhD student. So right now at Pitt, I am actually located, my main department is industrial engineering, but I do have joint appointments in mechanical engineering and chemical engineering, actually. So yeah,
Very cool.
what I think is really interesting is just that a lot of research now is very interdisciplinary. So a lot of these traditional boundaries that you might think of for departments are kind of breaking down. And I think that's really where you get a lot of interesting new research, interesting new work being done.
That's a great point, and I definitely want to dig into that a little bit. In particular, I know that when I was considering the opportunities available in academics, one of the things that I think frustrated me a little bit was that if I was going to join a math department, which is where I was headed, uh, they really only prized the publications in math journals, or at least some of the places I spoke with felt that way. So the opportunity to do really interdisciplinary research was complicated. You feel like your department has embraced a much more interdisciplinary philosophy?
Yes, yeah, I think the University of Pittsburgh, but I think that's probably a general trend across universities as well. I mean, I see a lot of research groups where the PhD students inside that research group just really span a wide variety of backgrounds and disciplines, and are getting their PhDs in different uh, different areas.
Makes sense. Makes sense. We're seeing a change. We're seeing an evolution of
Yeah.
different universities to meet the exciting research opportunities that are available to us today. Speaking of which, tell us about your research, Paul. Obviously, we got to see it at summit.sigopt.com back in November of 2021. But now, give us a little refresher. Tell us everything that led up to that,
Sh-
and
sh-
tell us how you got here.
Sure, sure. So a lot of my research has been in functional materials. It's been in nanomaterials as well. So just novel new materials and trying to create new functionalities from these materials. So nanomaterials are very, very small. If nano means 10 to the minus 9. So to give you an idea of the length scale of that, if you have a meter, which you're probably familiar with, you go 1,000 times smaller, you have millimeters, which are, like your wires, charging cables. You go another 1,000 times smaller, those are microns. And so, for example, red blood cells that are in your blood are just a few microns in diameter. And then another 1,000 times smaller than that would be nanometers. And individual atoms are about a tenth of a nanometer in diameter. So a good uh, instructive example would be that if you take an apple, and you enlarge that apple to the size of the Earth, then the atoms in that apple are now about the size of that original apple. So apple is to Earth as atom is to apple. So that just kind of gives you a rough idea of how incredibly small atoms are. And those are the types of length scales that we're working at, nanometer length scales.
Boy, oh
So
boy, that is really something right there. So when you say that you're working on this nanometer length scale, you're talking about objects that have sort of, I might even say, like a countable number of atoms
yes,
contributing to
yes,
elements of it.
yeah.
That's kind of
So
shocking.
yeah. So we're talking maybe tens, hundreds, thousands, 10,000s of atoms. But yeah, the
Hmm.
number of atoms is um, not very large, and
Yeah.
because of how small things are, you have a lot of interesting new properties and functionalities that you can take advantage of.
So along those lines, then, when we talk about the idea of things being small here, uh, there's like a couple ways I could see that going. You're not talking about just making a really small tie or shirt or something like that, right? You're not
Right,
saying, "Oh,
right.
I'm going to make a shirt that's 10." What are we talking about? What does this mean? That you're making something that's 10 to the minus 9 meters.
Yeah, so we're making things like transistors. Sorry, we're not actually doing that in my lab. But that is something a lot of people are working on. So
Certainly,
transistors,
people at Intel, I think.
yes,
Yes.
yes. So trying to make the little switches that go into your computer processing unit smaller, packing more devices into a smaller area, having more memory capability, things like trying to create new sensors that can sense uh, molecules, individual molecules, or molecules at
Wow.
very small concentrations, um, things like that. So yeah, there are also a lot of interesting possibilities with light. So visible light, the light that you and I humans see, is around 400 to 700 nanometers in wavelength. So a lot of these nanomaterials are smaller than that or on the same length scale as that. So you can um, create a lot of interesting ways of interacting with light. And
Oh,
that's,
oh,
sorry, go ahead.
no, along those lines, then, what research have you been doing specifically to think about these questions around light and how light can be manipulated or interacted with in some effective fashion?
Right. So one of the big areas that we've worked on is solar. So can we create new structures that convert sunlight into electricity with higher conversion efficiencies? Can we create new materials or new solar cells that use less material so they could be potentially less expensive overall? Um, there are other types of light sensors where you want to capture light in specific parts of the spectrum. So you may want to capture, for example, ultraviolet light or infrared light, for example, and then filter out other parts of the spectrum. So those are all types of applications that we've worked on. So one of the big applications, which is what I talked about at the SigOpt summit, is also related to light and nanostructures, and that is basically creating new types of glass which allow light to pass through. So the glass is very anti-reflecting um, across a wide variety of wavelengths, as well as a wide variety of incidence angles. And then we also looked a little bit at other types of functionalities that we can implement into that glass, things that could be beneficial depending on the application, things like self-cleaning or anti-soiling, stain resistance, or anti-fogging. So because we're creating nanostructures that are smaller than the wavelengths of light, that allows us to um, play around with some of the material properties that uh, enable very good anti-reflection.
In this search for designing glass that has these properties, how does SigOpt play a role?
Yeah, so SigOpt has been extremely useful in our materials work. So I think one of the big challenges with most experimentalists is that they rely on physical intuition a lot. They may be working with, you know, 10, 20 various possible parameters that they can adjust or tune. But in the end, they'll probably fix most of those parameters and just systematically vary one of them, one or two of them. So they really end up, a lot of experimentalists just really end up doing experiments in a very limited part of the entire design parameter space. So SigOpt has enabled us to really search more thoroughly in a very fast and efficient manner the very high dimensional design or design parameter space to look for material designs that are optimized for anti-reflection, for self-cleaning, um, for low haze, for example.
And I've been very excited over the years now to be able to work with you on this particular project. And it's given me an exciting opportunity to dive into the world of additive manufacturing at a nano scale, which is not something I had any background in whatsoever before. So I want to thank you for bringing us into this world. And
Sure.
then, in addition to that, you've given significant new opportunities here at SigOpt. As somebody who's collaborated with us on these new features of our product, features designed to serve the needs of people who are both building things fully in a wet lab in some sort of physical experimentation process, and also for people who spend some amount of time doing computational simulation, which then leads to an eventual physical manifestation or maybe a subsequent very small physical experimentation
Right,
series.
right.
Maybe you could tell us about how this is working for you, how this iterative process is working for you, and in particular, this use of the computational side of things. Maybe you can give us just a little more detail on that.
Sure, sure. So yeah, I mean, one of the things that we've worked on is electrodynamic simulations. So just doing simulations to see what are the different types of what types of structures provide for the best anti-reflection properties. So this could be, for example, across the visible spectrum, which is important for things like displays, or across the solar spectrum, which is more important for solar panels. And then we've also looked at minimizing reflection, basically having as much anti-reflection as possible for high incidence angles. And this is important because for things like lighting or even for displays, you don't want the light to be so directional necessarily. There are certain applications where you might want the light to be more directional if you have, for example, a privacy screen and you don't want other people to be able to look at what you're looking at. But for something like a TV, things like lighting, you generally want to have a profile that is more uniform in all directions. So we for solar, this is also important because most solar installations are fixed. They're fixed at some angle on your roof. They're usually not tracking, and the sun moves through the sky during the day, and then you also have some scattered light hit your solar panel from all different directions. And so being able to capture that light efficiently when the sun's not necessarily directly normal to the solar panel is also helpful for improving its overall efficiency.
Hmm.
So yeah, we've done a lot of work together, just coming from a new area, just being able to integrate some of our tools, things like MATLAB and Mathematica, and trying to integrate them with the SigOps tools has been useful. And also just having new types of functionalities, I think, has also been useful for us. So, for example, I think SigOpt basically, a lot of the parameters are essentially just limited by machine precision, where, when you're doing actual experiments, that sort of precision is really not needed for a lot of the parameters that you're tuning. If you change a gas by, you know, a
10 to the
few,
-5 pascals, then it's
yeah, if you change the
yeah, it's not.
pressure by a little bit, it's not going to change the results very
Yeah.
much. So that's uh, also been an interesting new implementation. Being able to do stuff with multi-objective optimization has also been very helpful. So in a lot of materials, a lot of materials design work, there are trade-offs between various objectives that you're trying to optimize. So understanding, where those trade-offs are and what the limits are in terms of Pareto frontier have been useful, and being able to visualize that.
Hmm.
Um, and also, yeah, just a lot of the visualization tools I think have been also very helpful. Just understanding your data, uh, understanding how the Bayesian optimization process is helping you move closer to a better design has all been very helpful.
Good to hear. Very, very good to hear. Let's talk what's going on. It's 2022 now. You've got big things coming up. I know one thing I'd like to take a moment to advertise. We'll be presenting digitally, unfortunately, but presenting a little workshop paper at AAAI coming up at the end of February. It'll be on the use of some of these new methodologies for some OLED design. Tell us, in addition to that, what else is going on for you this year? What else is exciting?
Yeah, so you may have heard that 2022 is the Year of Glass. It's been designated by the United Nations as the Year of Glass. So I think a lot of universities, museums, a lot of companies are really promoting all the different types of glass that are out there, the different applications. So yeah, I mean, wherever you are, I think just be on the lookout for that. I think there's probably opportunities to visit your local museum and see different glass displays and things like that. Um, Glass is ubiquitous, and if you're watching this on your computer, you're looking probably through a glass a display that has glass on front of it, on the front of it. The
Yep,
internet signal is being transmitted through fiber optic cable, which is glass.
true.
So yeah, the glass has been has really
Big
transformed the way we
things.
live. Yes.
Absolutely. Absolutely. Very
Um,
good point.
yeah. The other thing that has been big, which about, is this new National Science Foundation Center that both the University of Pittsburgh and Case Western Reserve University have started up. So this National Science Foundation Center is an IUCRC. So that stands for Industry University Cooperative Research Center. And we've been cooperating with various companies that have joined the center, government labs. And so we are basically in the center trying to bring data science methods towards materials manufacturing, understanding how materials properties and functionalities change over time, and understanding how what's causing these properties and functionalities to change, what's causing it to degrade, and trying to see if there are ways in which we can improve the materials so that they last longer. So just for an example, a solar panel commercially right now is expected to last about 25 years if you put it up on your roof. After about 10 years, it's not going to be able to convert sunlight as efficiently as when you initially installed it, perhaps around 90% of its power conversion efficiency initially, and then around 80% after 20 years. So then after about 25 years, it may be time to get a new solar panel. So we're using these new types of data science, machine learning methodologies to try to study how the solar panel is changing over time. So obviously you don't want to do studies over 20 years or 25 years. So there are a lot of accelerated protocols in laboratories where you subject your solar panel to, for example, temperature cycling. You'll heat it up and then cool it down, heat it up, cool it down. There's other things that you'll try to cycle quickly, exposure to humidity, exposure to ultraviolet light, some salt fog, which is basically humidity with some salts in it. So there are all these types of protocols for accelerated testing, and we want to try to understand how the results of these accelerated protocols correlate to real-world performance. And then we also want to understand, for example, the degradation mechanisms, what's causing these panels to lose that ability to convert sunlight into electricity, whether that's moisture getting in, oxygen reacting with some of the materials, whether it's cracking or delamination of some of the encapsulation. So yeah, the objective is to really extend the lifetime of solar panels. So can we make solar panels last 30 years, 40 years, things like that?
Yeah, absolutely. That's an exciting opportunity. That's a huge piece of research, not just sort of in the immediate term, but as you mentioned, long term. And obviously, I think that's a fantastic demonstration of bringing data science to bear in a field which traditionally may not have used so much of these classically just computer science tools. So I'd love to see that. How can people learn more about this IUCRC?
You can learn more about this IUCRC by going to our website. That is M as in Mary, D as in David, S rely.org. We also have a Twitter handle, so you can check us out on that. Yeah,
do you know what that Twitter handle is?
I think it's the same
Is it
thing.
MDS-Rely?
Yeah.
Very good.
So yeah, you can check us out. We have a big meeting coming up in April. Currently, it is scheduled to be in person in Pittsburgh, but yeah, depending on what happens, it might be virtual. But yeah, if the capabilities of the center, this idea of being connecting more with universities, other industry members, and other government labs is interesting to you, feel free to reach out and send me an email.
Very good. Very good. I am sure that many people who are watching this are thinking to themselves, gee, what a cool opportunity. Once again, everybody, that's MDS-Rely, RELERELY, .org. I'm very excited to be contributing my minor amount to it, and I am very excited to see what's coming up next for it. So once again, MDS-Rely.org. And today, this was Dr. Paul Liu joining us from the University of Pittsburgh. Thank you very much for your time today, sir. We are looking forward for all those exciting things coming the rest of this year and the years to come. All right?
All right, thanks, everyone.
Take care. If you have enjoyed these interviews and want to learn more, the description below contains the link to the show notes. There you will find links to the papers we reference, supplemental material, and a transcription. We hope to see you here next time on Experiment Exchange.